Hello, everyone, and welcome to today's webinar titled Anticipating the Next Outbreak, Monitoring SARS-CoV-2 and an Expanded Infectious Disease Panel by LCMS. This webinar is part of the 13th Annual Clinical Diagnostics and Research Virtual Event, and I'm Susie Valdez of LabRoots, and I will be your moderator for today's event. Today's educational web seminar is presented by LabRoots and sponsored by Thermo Fisher Scientific. For more information about Thermo Fisher Scientific, go to www.thermofisher.com. Now let's get started. Before we begin, I want to remind everyone that this event is interactive. We encourage you to first participate by communicating with other attendees using our new live chat feature during this presentation. You can find that live chat located on the left of your screen. Now, you can also participate by submitting as many questions as you want during the presentation. To do so, simply type them into the Ask a Question box and click Submit. We'll answer as many questions as we have time for at the end of the presentation. Now, you will also notice the speaker has provided a survey located at the right of the Ask a Question box. This survey will be available during the live session and the on-demand period. Now, if you have any trouble seeing or hearing this presentation, just click on that help desk button located at the top of your screen within the navigation bar or from the lobby. And finally, as a reminder, this presentation is educational and offers free continuing education credits. Click on that continuing education credits link located in the abstract tab from the menu at the left of your screen and follow the process to obtain those credits. I now present today's speaker, Dr. Richard Gibson, an application scientist at Thermo Fisher Scientific. For a complete biography of our speaker, please visit the presenter tab from the menu at the left of your screen. Dr. Gibson, welcome. You may now begin your presentation.
Hi, I'm Richard Gibson, and I'm application scientist for Thermo Fisher Scientific out in San Jose, California. And I'd like to talk to you today about anticipating the next outbreak, how we monitored SARS-CoV-2 and developed an expanded infectious disease panel utilizing LCMS. First, I'd like to give a bit of an overview on protein quantitation and why it's important. So protein quantitation plays a huge role in every stage of developing methods. The group that I'm in primarily concerned with developing clinical methods, but the upstream research and translational domains, proteomics domains, are vital steps in obtaining the information to be able to develop clinical protein quantitation methods. For example, protein quantitation is important in gathering information to understand the specific and effective defenses against viral infections, to identify distinct immune responses, such as with monoclonal antibodies, and to understand the variants of post-translational modifications. It's also vital in the translational proteomics domains, where unknown protein biomarkers that are early signs of viral diseases can be detected and quantified through label-free quantitation or with tandem mass tags. Clinical methods are built with some of this information, such as by using discovery data to choose targeted peptides and the transitions for bottom-up workflows, or to pick variants of interest to quantify, allowing clinical protein quantitation methods to present data that confidently assesses the biological state of a patient in a way that provides vital information. It's important to note that the quantitation of a protein can be performed in numerous ways, with each method having advantages and disadvantages depending on the situation. I'll be highlighting some situations where LCMS is ideal, but other methods such as immunoassays, like enzyme-linked immunosorbent assays, ELISA, and colorimetric assays, such as Bradford assays or Lowry assays, may be ideal for certain situations. LCMS has several key advantages, such as providing fewer false positives and negatives, and the ability to provide qualitative and quantitative data within one run. It's also able to detect proteins with different hydrophobicities and polarities, which combined with high selectivity means LCMS can be used to accurately and confidently quantify most proteins. As we can see, the number of LCMS protein quantitation publications has increased significantly throughout the past 2 decades. both triple stage quadrupole and high resolution accurate mass spectrometers used to routinely quantify proteins and provide high selectivity, specificity, and sensitivity, as well as providing robust and reproducible results. Workflows are very flexible and they're able to include numerous steps such as digestion, enrichment, and affinity capture, all of which, when combined with LCMS, allow for incredibly low detection limits of targeted proteins. These workflows also involve very short runtimes, down to a few minutes, which creates high throughput. The ability to target multiple proteins within one run allows us to create panels, and this allows methods which are highly profitable due to the high throughput and their relatively inexpensive reagents. So there are many different types of workflows that can be used to quantify a protein, one of which is top-down protein quantitation, where intact proteins are studied. This requires high-resolution, accurate mass spectrometers, especially when variants and post-translational modifications also need to be studied. One of the main advantages of top-down quantitation is that minimal sample preparation is required, which minimizes costs and also the time spent preparing samples. Proteins may also be quantified by global protein quantitation, which is the relative quantitation of many proteins within the same sample. An example of this would be protein profiling, in which the relative abundance of hundreds of proteins would be compared to decide if any were present in irregular levels. Higher concentrations of a certain protein could be indicative of doping, such as with erythropoietin, or health issues, such as a high concentration of amyloid beta 42, which are both indicative of Alzheimer's. Middle up or middle down protein quantitation involves the limited cleavage of a protein into its subunits, which allows post-translational modifications and sequence changes to be more easily detected and localized to certain parts of the protein. High resolution is still required for these applications, which are often used when variant profiling is required to understand the significance of the results. Finally, the one we're going to be looking at in this talk is bottom-up quantitation, which involves the digestion of the protein by a restriction enzyme, such as trypsin. The smaller mass of the generated peptides then allows a lower resolution mass spec to be used. Individual peptides from wild-type proteins or variants can easily be targeted using bottom-up mass spectrometry. In addition, heavy isotopes corresponding to the targeted peptides can be spiked into the samples and act as internal standards. This increases the certainty of our results, as well as allowing correction for matrix effects and for more accurate quantitation. So although bottom-up protein quantitation can be carried out using high-resolution accurate mass spectrometers, the higher sensitivity may be achieved using triple-stage quadrupole mass spectrometers. These provide robustness with ultimate consistency in day-to-day performance, sample-to-sample results, and user-to-user productivity. They're also very fast, which enables high throughput and faster analysis of complex mixtures. And they're very sensitive with high sensitivity for all molecule types, regardless of matrix complexity. They also provide high selectivity, which brings significant benefits for peptides in complex matrices. Within what we're going to be talking about in this presentation, we've used a triple-stage quadrupole mass spectrometer, which is the Thermo Scientific TSQ Otis MD mass spec. So this is a medical device, which makes it perfect for lab-developed tests. There's also numerous products you can use for sample preparation, which includes a variety of Dynabead immunoprecipitation kits that are available to allow the enrichment of proteins. So basically pulling your proteins out from the rest of the sample to create a purer thing for analysis. Protein A and protein G coated Dynabeads both allow enrichment of monoclonal antibodies. Epoxy Dynabeads combine any protein, making them ideal for less specific enrichment, such as just separating proteins from other components of the sample. and streptavidin, which can be used to enrich biotinylated antibodies. Antibodies with specificity toward certain proteins can also be coupled to these beads, allowing specific enrichment of a certain target protein. Although Dynabead kits are simple to use, they prove to be fairly labor intensive. Therefore, there are a number of different automated purification systems, such as the Kingfisher purification systems. The base one would be the Duo Prime, which is able to enrich 12 or 24 samples simultaneously. And there's also the Flex, which is suited for labs with higher throughput and can enrich up to 96 samples. And there's also the Apex, which is an upgraded version of the Flex with capabilities such as barcode reading, and the Presto, which is the premium product, also able to integrate directly with automated liquid handlers such as the Hamilton Star systems. There's also smart digest kits, which are available in a number of different enzymes, including trypsin. These are fast, reliable, and easy to use, so you can quickly generate peptides from your intact proteins. There's also custom peptide synthesis services where you're able to synthesize standard peptides, heavy labeled isotope peptides to use as internal standards, and also peptide libraries. If further sample cleanup is needed, there's also the Solar Micro SPE plates, which are available in a number of different hydrophobicities depending on your target protein, all the way from cation to anion exchange. There's also numerous different software packages for protein quantitation, such as Proteome Discoverer, which allows the development of discovery methods, as well as data acquisition and bioinformatic analysis. The addition of the Chimeris artificial intelligence algorithm that searches an online database has doubled the number of peptide identifications, simplifying the process of selecting transitions to be utilized in quantitation studies. TraceFinder software allows method development, data acquisition, and protein quantitation for Thermo Fisher TSQ triple quadrupole instruments, and also the high-resolution accurate mass Orbitrap Exploris and Tribrid mass spectrometers with seamless method transfer between the instruments. Along with Tune software, broad mass spectrometer range and sample preparation kits, this provides a full one-vendor protein quantitation by LCMS solution. So as previously mentioned, all of the work in this talk will be following bottom-up workflows, where a restriction enzyme, such as trypsin, is used to digest proteins in a sample, generating peptides. These peptides may then be used as signatures for their respective origin protein, with at least several peptides not likely to be present in non-targeted proteins being required for accurate quantitation. The targeted peptides must have favorable properties for LCMS analysis and may either be selected from discovery data using high-resolution accurate mass spectrometry, or through mass spectrometer or through in silico digestion. The smaller size of peptides compared with intact proteins can significantly improve the ability to detect them if they can be successfully differentiated from other peptides by the liquid chromatography gradient and this mass spectrometry detection method. To do this, we must go beyond MS1 analysis and use tandem mass spectrometry. This is due to the ambiguity of many signals from coeluting isobaric peptide species. Therefore, we must use a targeted peptide method, such as selected reaction monitoring or SRM, to confirm signals corresponding to our target peptides. Triple stage quadrupole mass spectrometry, SRM methods, allow the separation of precursor ions corresponding to the expected mass to charge ratio of our target peptides from much of the excess noise. The second stage of the quadrupole then allows fragmentation of the selected ions before product ions corresponding to expected fragments are targeted to ensure the correct peptide is detected. So now, given a bit of a introduction into what protein quantitation is, and specifically bottom-up protein quantitation, I'd like to move into the part of our talk regarding quantitation of SARS-CoV-2, so the virus that causes COVID-19, by LCMS. COVID-19 is a serious global health crisis that's resulted in over 6.5 million reported deaths. So at the height of the pandemic, PCR was unable to keep up with the demand for testing due to the shortages of reagents, equipment, and trained personnel, highlighting the need for analogous techniques to provide COVID testing, which wouldn't replace PCR, but would act as complementary techniques to PCR to take up some of the slack in the testing. LCMS systems have previously been demonstrated to allow detection and quantitation of viruses. So we're set about working on developing a peptide quantitation method that could be used to utilize LCMS systems in labs during any future pandemic, where LCMS systems are unlikely to be being fully utilized. This could not only just provide a vital public health service, but also an alternative stream of revenue for customers during a time when many traditional revenue streams are low. Consideration when developing this method was taken into account with time constraints, so the method needed to be quick. We decided to primarily target the nucleic capsid due to its internal position in SARS-CoV-2 virus, reducing the likelihood of any mutations or post-translational modifications occurring. This thereby increases the certainty in our results. Also considered were numerous antibody enrichment techniques that can allow separation of either the target proteins or target peptides from more complex samples. So there was some publications already when we started this work on detection of SARS-CoV-2 by LCMS. One of these publications was by one of our collaborators, so the Fleury Lab in Brazil, published a Nature paper where they showed a complete workflow for the detection of SARS-CoV-2 from clinical sample cohorts. The entire workflow was automated and it utilized magnetic bead purification and online turboflow cleanup of patient-acquired samples. Transitions were selected using data acquired by Q-Exactive high-field instruments, so high-resolution accurate mass spectrometer, as well as from in silico digestions by Skyline, which is a third-party software that's freely available. This was used to develop TSQ-OTIS-based methods for the detection of SARS-CoV-2 and was sensitive enough to detect 84% of cases detected by their in-house PCR testing. Two specific peptides were targeted, and detection limits of below 50 femtomole on column were achieved for both of these peptides. The method was also demonstrated to not detect peptides in clinical specimens from other coronavirus strains, rhinovirus, enterovirus, and influenza viruses, which suggests that there's no assay interference. In addition, utilization of a multi-channel Thermo Scientific TLX4 allowed significant throughput with over 500 samples able to be ran within a 24-hour period. We decided to create our own method with several aims. So we wanted to target more peptides, and we also wanted to improve the detection limits in order to reduce the number of positive cases that would be missed. Our test samples consisted of spiking recombinant SARS-CoV-2 spike and nucleocapsid proteins into nasal fluids, which were then placed onto nasopharyngeal swabs and incubated in viral transport media. This was just to mimic actual sample collection as closely as possible within our lab, where we weren't able to use actual real samples due to health and safety. Samples were then vortexed, precipitated with ice-cold acetone, centrifuged and dried, resulting in isolated proteins from the recombinant targets, as well as any proteins present in nasal fluids or viral transport media. The isolated protein samples were then enzymatically digested to generate peptides with a Smart Digest trypsin kit. Samples were then analyzed by LCMS, and each targeted peptide was quantified with TraceFinder. In this study, a second analogous workflow was also run in which the recombinant target proteins were spiked into saliva that was then incubated in viral transport media. The rest of the workflow was then identical and was done to demonstrate the feasibility of using our method to quantify proteins from a second viable collection matrix. The whole workflow was successfully implemented within around 2 hours. I would like to go into a few details about our liquid chromatography and our mass spectrometry method now. So the liquid chromatography, LC conditions, are listed here. We used a Hypersil Gold C18 column, which is a commonly used column for peptides. And we had 10% IPA in mobile phase B, which was included, so the organic phase, which was included as it allowed us to almost completely eliminate carryover between runs. The LC method gradient was optimized to provide clear separation between each nucleocapsid and spike peptide, whilst providing a quick runtime. All this was done using the Vanquish MD HPLC, so a medical device liquid chromatography system that's ideal for lab-developed tests and when paired with an MD mass spectrometer. For the mass spectrometer, we used the TSQ Altis MD, so again, a medical device. Here we've listed the source and experimental conditions, which were all fully optimized to allow for the most efficient detection and quantitation of target peptides delivered to the mass spectrometer from the upstream LC. The transitions were also fully optimized with one Q1 precursor transition and 3 Q3 product ion transitions for each peptide. Q1 precursor transitions correspond to a master charge ratio of either the second or the third charge state of the target peptide. These are selected, passed to Q2, so the second stage of the quadrupole, which acts as a collision cell, resulting in the fragmentation of the peptide. Ions corresponding to the 3 most easily detected fragments are then isolated in Q3. Being able to observe 3 of these fragments allows us to confidently confirm the presence of the corresponding peptide, and confirmation of 3 signature peptides from an individual viral target then allows us to confidently identify the viral target. Once we developed the method, we also spiked stable isotope standard versions of each target peptide into either the nasal fluids or the saliva at the start of the process. These were used to confirm the retention times of the target peptide and also to allow absolute quantitation of each detected peptide, as we know exactly how much was included. They're differentiable from our target peptide due to the presence of heavy labels, which shifts the mass of the transitions by a known amount that may then be searched for within the same sample run. We then prepared calibrants that included varying concentrations of the target proteins and fixed concentrations of the target peptides. By examining calibrants of different levels, we were able to determine the limits of detection for each peptide in both nasal fluids and saliva. The limit of detection was just defined as the lowest concentration, in which 3 replicates were confidently differentiable from noise, with at least 4 times the intensity of the peak. Tracefinder software was able to use these calibrants to produce calibration curves that were then used to determine limits of quantitation. Concentrations not meeting the limits of detection were discarded, and then the next lowest concentration would be discarded until a specific criteria were met. These included data providing a close fit to the line with an R² of greater than 0.99, and every calibrant achieving RSDs and CVs of less than 15%. Each of our 6 targets were demonstrated to be absolutely quantifiable, down to either sub or low on femtomole on column limits, femtomole on column limits. So in summary of this first part of the work, a minimal sample preparation method involving the precipitation of proteins from spiked nasal fluid and saliva samples allowed the quick and economic quantitation of each peptide down to sub or low femtomole on column levels for 6 SARS-CoV-2 peptides. One of these peptides was from the externally located spike protein, and 5 were from the internally located nucleocapsid protein. Linearity was demonstrated from the stated limits of quantitation up to 100 femtomole on column, and each calibrant was prepared and ran in triplicate. R-squared values of each fitted calibrant were greater than 0.99, and CV values were less than 15%, demonstrating the ability of the TSQ Altis MD to reliably and accurately quantify low levels of protein in different matrices to sub-femtomole on column levels. These results were published as a technical note, highlighting the capabilities of the instruments to absolutely quantify 6 peptides from SARS-CoV-2. We then decided alternative sample preparation techniques should be explored in order to overcome potential issues due to the added complexity of if we're actually going to use patient-acquired samples in the future. So our next step was to include stable isotope-labelled standards captured by anti-peptide antibodies, which is also known as the SISCAPA. This is a peptide enrichment method that is placed after the digestion step and allows the separation of target peptides from almost anything else in the sample, creating ultra-pure samples. This technique utilizes rabbit antibodies that have strong affinity towards epitopes in the target peptides. They're commercially available from a third party and are pre-coated onto magnetic beads. This allows easy separation from the sample after peptide binding with a magnet. SISCAPA beads were commercially available with specific selectivity towards 6 peptides from the nucleocapsid of SARS-CoV-2. We purchased the 4 that corresponded to peptides in our previous study. The ADET peptide was also able to enrich the KEDET peptide, as this was just one miscleavage difference. So we were potentially able to target 5 peptides from the SARS-CoV-2 nucleocapsid protein. As previously noted, the SISCAPA peptide enrichment step occurs after digestion and before load injection onto the LCMS system. Digests are incubated with a mixture of each SISCAPA bead, which are then washed to remove anything not bound to the bead antibody complex. After several wash steps, bound peptides are eluted from the complex by a more acidic solution. The SISCAPA complex is then removed by a magnet, and the ultra-pure sample containing the target proteins is examined by LCMS. The addition of this workflow increased the time of sample preparation by around 90 minutes, but resulted in the removal of the majority of non-targeted peptides, trypsin, and other sample components. It also had the added benefit of concentrating our samples by approximately 40-fold compared with the previous method. The extra purity of the samples allowed the runtime to be shortened to 2 minutes, while still providing analytical separation of peptides. All other LCMS conditions remain constant from the previous method, except retention times, which had shifted forward due to increasing the gradient. This method resulted in similar on-column LODs and LOQs to the previous method for 3 of our targeted peptides, which allowed the absolute quantitation of SARS-CoV-2's nucleocapsid protein down to 2.5 femtomole on column. However, due to the pre-concentration of the sample by SISCAPA, this is in fact an increase in detection and quantitation limits of between 10 and 80 times for each of these 3 peptides when you consider the concentrations in the starting nasal fluid samples. This work was then published again as a second technical note, which demonstrated the successful peptide enrichment for enhanced detection of 3 peptides from SARS-CoV-2. This was done within a quick, reliable, and robust 2-minute LCMS method. LODs and LOQs were in the low or sub-femtomole on column range, and we saw an increase of over 10-fold in detection limits from the starting concentrations in nasal fluids. So now we've developed our first analogous workflow. We wanted to look into further antibody enrichment techniques, which would target the proteins, so enriching the proteins. So to do this, we used a antibody enrichment technique where antibodies are coupled to magnetic beads, and used to enrich targeted proteins. In this case, the enrichment step would be placed before enzymatic digestion. Removing non-targeted proteins before digestion can potentially reduce digestion times, as there are less untargeted proteins in there to take up the enzyme, and allow coupling of already developed Kingfisher automated purification system protocols for our sample preparation. Preliminary work was carried out showing that protein A/G, and streptavidin, Dynabeads, coupled to SARS-CoV-2 antibodies, could efficiently enrich SARS-CoV-2's nucleocapsid protein. One further benefit of this workflow is that antibodies with affinity to specific proteins are much more prevalent than peptide-specific antibodies. This gives an increased number of potential targets and much quicker method development for future infectious disease outbreaks. Due to the potential to detect multiple infectious diseases with this workflow, we decided to see if we could expand this approach to target proteins from multiple viruses within one workflow. Expanding to an infectious disease panel is beneficial, as patients tested for COVID could potentially mistake the symptoms of another respiratory virus for COVID. Being able to identify other infections allows the patient to isolate as necessary, and also increases the certainty of being negative for other viruses if you tested positive for a specific one, which would explain your symptoms. So now I'll move on to the third part of the talk, which is the development of a respiratory infectious disease panel. The listed common respiratory infections on the right all have symptoms that may be mistaken for COVID-19. In addition, they all contain a centrally located nucleocapsid protein, which, as previously noted, is generally highly conserved between variants of the same virus, and is much less likely to contain post-translational modifications than other protein biomarkers. Therefore, targeting the nucleocapsid proteins of multiple viruses within one run simultaneously is a workflow that we believe is most likely to provide robust testing methods for a panel. Literature reviews were able to identify a number of unique targets favorable for LCMS analysis in SARS-CoV-2, influenza A, influenza B, RSV, and human coronavirus, and antibodies were commercially available with specificity towards each of these targets. So after confirmation that the antibodies could successfully and simultaneously enrich each of these target proteins, optimization of the immunoprecipitation time was carried out, followed by optimization of the digestion times and confirmation that on-bead digestion was efficient. This resulted in antibody enrichment by immunoprecipitation in only 30 minutes, while simultaneously reducing the required digestion time by 1 hour and 15 minutes. In addition, the immunoprecipitation step was shown to work just as efficiently in viral transport media, thereby removing the need for a protein precipitation step. Combined, these optimizations meant the whole workflow took less than 1 hour, including the LC-MS detection. Although this was the LCMS method was increased to 5 minutes as we needed to change the gradient to allow for chromatographic separation of each of these target peptides. In total, this method was able to target 5 nucleocapsid proteins, each of which had 2 or 3 target precursor transitions. The final workflow involved the same sample collection in viral transport media as previously shown for the other methods, with the addition of the antibody enrichment steps. Biotinylated antibodies for each target protein were incubated in the viral transport media, where they bound to the corresponding protein targets. The antigen biotinylated antibody complexes were then immobilized on streptavidin magnetic beads and separated from the solution with a magnet. After several wash steps, the antigen antibody complex was digested by trypsin while still attached to the beads. This resulted in the release of the majority of the peptides from the complex, including the peptide targets for each of the viruses, which were then analyzed by an LCMS method. Calibrants were then used to assess the performance of the method. It resulted in sub-femtomole on column or femtomole on column, LODs and LOQs for 12 peptides from 5 different viral targets. Analytical separation of the peptides was demonstrated, and internal standards were used to confirm retention times and allow for absolute quantitation of each of these targets. The data was then published as a technical note, which demonstrated absolute quantitation of peptides from 5 different infectious disease targets, so influenza A and B, SARS-CoV-2, RSV, and human coronavirus. This was done within a quick, reliable, and robust 5-minute LCMS method, and used protein enrichment by Dynabeads, which significantly reduced sample preparation time to less than an hour. LOQs were either at 1 femtomole or sub-femtomole on column range, showing exceptional detection limits. To simultaneously detect peptides from 5 different infectious diseases within 1 hour. So I'd like to include a quick comparison of the benefits of each of these protein or peptide enrichment methods. So the peptide enrichment method does provide quicker LCMS runs, although the sample preparation time is longer. So the exact capabilities of an individual lab would thereby determine which one is more time efficient. The peptide enrichment beads are fairly uneconomical, and the protein-specific antibody and Dynabeads are able to provide a more comprehensive test for only a slightly higher cost. In addition, the Dynabead method has more potential targets and is likely to be easier to pivot from in the case of future pandemics. However, the ability to load concentrated samples onto the LC systems, the peptide enrichment method, does decrease the viral load needed for a positive test. So in summary, for this work that's done, we demonstrated the absolute quantitation of SARS-CoV-2's nucleic acid protein and a peptide from the spike protein from spike nasal fluid samples. We were able to do this within a 2-minute run, which had a 30-second data collection window. This therefore creates the opportunity to move to a multi-channel method, which would potentially be able to run a sample every 30 seconds if you've got 4 channels. We demonstrated the detection and quantitation at low or sub-femtomole on column concentrations with each of these methods. We showed analogous protein enrichment methods, which were developed for quicker sample preparation, and were able to detect an infectious disease panel rather than just the SARS-CoV-2 target. This resulted in robust, quick, and reliable targeted protein quantitation workflows for infectious diseases in spike nasal fluids. So this work has demonstrated that triple-stage quadrupole mass spectrometry offers superior analytical performance for targeted peptide quantitation, and that the TSQ Altis MD mass spectrometer provides exceptional sensitivity and selectivity over a wide dynamic range. We also showed that automated workflows can enhance productivity and turnaround time. The TraceFinder software provides an integrated and automated workflow all the way from data acquisition to reporting. And if we were to incorporate the Kingfisher purification system, we're actually able to reduce the hands-on time of these methods significantly. So I'd like to acknowledge my group. Ifon Song did a lot of the expansion of the method into an infectious disease panel. Our manager, Stephanie Samra, was involved in all of this work. But I'd like to thank the wider group, the whole wider group, who have had a lot of input into this work with a lot of suggestions and also help in preparing this presentation. So thank you to them. I would also like to thank everyone who's listened to this presentation. I hope that it's been informative, and if any of you have any questions, I'll be very happy to answer these questions now. Thank you.
And thank you, Dr. Gibson, for that informative presentation. We will now start the live Q&A portion of this webinar. And if you have any questions you'd like to ask, please do so now. Just click on that Ask Question box located on the far left of your screen. So let's get started. It looks like we already have a couple of questions coming in. Our first question, Dr. Gibson, is which protein in an infectious disease target provides the most robust target due to the presence of less mutations?
The nucleic acid protein is located in the center of most viruses. Therefore, there's less mutations, less post-translational modifications. So you're going to get less variation in your peptide targets, and you're going to be able to robustly detect them and be fairly confident that there's no mutations. Whereas other parts of the virus, like the spike protein, they've really commonly got mutations. And in fact, all of the common variants of COVID-19, SARS-CoV-2, have mutations on the spike protein. Some of them have mutations in the nucleic acid also, but it's less common.
Thank you so much. And we have another one coming in from our audience. Why can't we just rely on PCR testing during future pandemics?
PCR testing is great and it's very efficient. It works fine. But there were times during the last COVID pandemic, so towards the start of the pandemic, when people weren't really prepared for it. There was a shortage of reagents, so we need other testing methods that use different reagents that can easily be developed and used when we can't do PCR. And also because of the demand, there's only a finite number of PCR machines and also people trained to use them. So we do need methods in other areas, such as LCMS, just to take up some of the slack in testing, really.
Dr. Gibson, I want to thank you for your time today. Do you have any closing remarks before we go today?
No, I just hope that everyone enjoyed the talk. And if there's anything you want to know, just email me. It's richard.gibson@thermofisher.com, and I'm more than happy to answer anything, talk about anything, and also for any suggestions. If anyone wants to just suggest anything or tell me anything, feel free.
Well, I want to thank you again for your time and for your important research. And before we go, I want to thank our audience for joining us today and for their interesting questions. I'd also like to thank our sponsor, Thermo Fisher Scientific, for sponsoring today's webinar. Questions we did not have time for today and those submitted during the on-demand period will be addressed by our speaker via the contact information you provided at the time of registration. And this webcast can be viewed on demand for 2 years until November 9th, 2024. LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Until next time, take care, everyone, and bye-bye.
Thank you.